not sharing? Can anyone
Yes,
see?
I can see the slides. It's
Okay.
fine.
All right. Thank you. I can't seem to change the slides still. Yeah, I'm trying.
Hey, everybody. Sorry, I just got in. I was having a problem.
Yeah, I'm trying. We're having a lot of problems.
Oh,
There we go.
okay.
Okay, so we do have, I just want to tell a little bit about FLATE. That was Ernie Friend, our new FLATE director. And I will be moving to a senior advisor position, or I am moving to senior advisor position and helping Ernie take the reins of the work we do with the Florida Department of Education and Florida Makes and the Florida Makes Network. So our vision is still to drive the world-class manufacturing workforce education in Florida and elsewhere as well. And I have 2 slides for that. And our work, all right, can you see these, Daniela?
Yes. Are you still in the first?
Do you see FLATE's work?
No,
got so
I
many
see
people
only
talking.
the first slide.
You see the first slide. So I'm on the 4th slide and nobody can see it. So how about if we just abort the talk about FLATE, and I'll turn it over to Tae-Sung to introduce himself and his presentation so we don't lose any more time.
Good
So I'm
idea.
gonna stop sharing my screen, hopefully. I'm not sure why I have so much technology.
Now is okay.
Issues right now, but let me stop sharing this. And
Somehow it's working now. I can see FLATE works.
well, I think we'll just go ahead and move on. And now this is advanced sharing options. I don't want that. I just want to stop sharing. Here we go. Sorry. So you ready, Dustin? We'll just forget that I said anything today and just move on to our presentation. You should have be able to share your screen.
Okay, yeah, let me try to share my screen. Can you see my screen now?
Yes.
Okay, good.
Hopefully everyone else can.
Is this in the presentation mode right now?
Yes.
Okay, perfect. So hello everyone. So this is Da Zhongwu. I'm an assistant professor in the Department of Mechanical and Aerospace Engineering at the University of Central Florida in Orlando. So today it's my pleasure to share with you some of my research on applications of machine learning in smart manufacturing. So today I'm going to talk about 3 research projects we completed at UCF. I will briefly talk about them, go through them one by one, and feel free to interrupt me during my presentation if you have any questions. And I will not cover all the technical details like the mathematics behind the machine learning algorithms, but I will focus on the applications of these algorithms in the manufacturing field. So first of all, I want to talk about directed energy deposition. The acronym is called DED. So this is one of the metal 3D printing process where a focused energy source such as laser, electron beam, or plasma arc is used to fuse metal materials. And actually there are quite a few advantages of this directed energy deposition process. For example, actually it will reduce material waste, actually, and also it allows for very high printing speed, and it has so-called multi-material 3D printing capability. And due to these unique advantages, so the market for the DED technology or the DED machines will reach actually $700 million by 2025. And there's a wide range of applications of directed energy deposition process. So, but as you can see here, there are several industries where this process or technique has been heavily or extensively used, such as including aerospace, oil and gas, defense, and architecture industries, because this process can actually repair very high-end, expensive, damaged parts, such as this turbine blades, as you can see from these two figures, before and after repairing with a directed energy deposition technique. And also this technique can be used to modify parts more effectively and efficiently. So however, there are actually also some disadvantage or downside of this technology. For example, like similar to other metal additive manufacturing processes, the DD process will introduce defects due to a gas trapped in the metal powders, keyholes, lack of fusion, and rapid solidification. As you can see from these SEM images, so you can see sometimes even pretty large voids introduced by this process. And actually, as I mentioned before, so these defects actually are affected by a so-called melt pool formation process during the DD process, such as melt pool temperature. And this melt pool refers to the spherically shaped area in the vicinity of the laser and the metal or material interface. And there are several challenges associated with this process. So one is the traditional or conventional physics-based models, such as finite element analysis, which you might be pretty familiar with, are usually not accurate enough to actually capture or detect these defects introduced by this process due to the very complex heat and mass transfer phenomenon within a melt pool. And our objective for this project is to develop machine learning algorithms or data-driven predictive modeling approaches to predict melt pool temperature in real time. So I will briefly talk about two algorithms, machine learning algorithms we implemented and tested for this research. The first one is called extreme gradient boost or XGBoost. So this is actually, as you can see, it's a tree model. So we actually grow hundreds or thousands of decision trees. And then these decision trees will help us to actually predict melt pool temperature. And this melt pool temperature will significantly affect defects, as I mentioned before. And the second algorithm is one of the deep learning algorithms. The previous one, XGBoost, actually is a machine learning algorithms. And long short-term memory, or acronym is LSTM, is one of the most effective deep learning algorithms. The reason why we chose to implement LSTM is because it keeps track of the long-term dependencies in time series data. As you can see here, actually the sensor data we collected is actually time series data. That's why we chose to implement this deep learning algorithm rather than other deep learning algorithms, such as one of you probably are familiar with, like a CNN, convolutional neural network. And here is two photos of our experimental setup. So on the left, you can see this is one of the lens 3D printing system equipped with an infrared camera. As you can see here, this is an infrared camera which can actually capture thermal image of a melt pool formation process during the DD process in real time. And on the left, you can see this is the actual thermal image captured by this thermal camera. And we actually fabricated several specimens, so-called thin-walled structures, using this DD machine. And the raw material of these structures actually is a nickel-based alloy, Inconel 780, which is very common actually in industry. And the substrate material is low-carbon steel. And you can see from this figure on the left, this is the build direction from bottom to up. And also, this is the implemented this zigzag two-pass strategy. And on the left, you can see the actual 3D printed thin wall specimens. And we fabricated in total actually 25 specimens, thin wall structures, using varying process parameters. And here I only provide some of the most important parameters, such as laser power, scan speed, power feed rate, power, and also laser spot diameter, hatch space. And here we actually, in order to reduce the total number of experiments, we only varied these two key parameters, laser power and scan speed. And these are the most important parameters that will affect printing quality. That's the reason why we only varied these two parameters. And also, we use actually 24 data sets to train our machine learning model, and then test and validate the accuracy of this model using the remaining 1 data sets, as you can see from here, this table at the bottom. And here are the experimental results. So you can see at the top, we plotted the actually temperature, multiple temperature versus time. And this red curve represents the actual observed temperature by the thermal camera. And also these dashed black and blue curves represent the predicted temperature, multiple temperature by the XGBoost algorithm and the LSTM algorithm. So as you can see, if you take a closer look at this figure, this plot, the predicted results actually are in very good agreement with the actual multiple temperature captured by the thermal camera. And further, we quantify the prediction accuracy for these two algorithms in terms of root mean square error, RMSE, and also mean absolute percentage error, MAPE. And these are the two commonly used error metrics to quantify the accuracy of a machine learning algorithm. And further, we want to quantify or evaluate actually the training efficiency of these two algorithms and see how long it will take to train effective machine learning models. So you can see if you compare these two algorithms, both of them achieved pretty good prediction accuracy in terms of RMSE and MAPE. So RMSE, the lower or the smaller the better, and also MAPE also is the smaller the better. And the training time, of course, also smaller the better. And you can see pretty much all of these black dots fall onto this 1-to-1 ratio straight line. And if you take a closer look at these two photos of two figures, we plotted the predicted temperature versus observed actual multiple temperature using these two algorithms, which is slightly different from the first plot. And also you can see in terms of training efficiency, this deep learning algorithm, LSTM, takes longer time than XGBoost, although actually the prediction accuracy is slightly better or higher than XGBoost. So in other words, there's some trade-off you need to balance when you choose the right machine learning algorithms to train your model. And we further compare our prediction accuracy or our results with the state-of-art methods reported in the literature. So here I only list 3 references. We compared with a closed form analytical model reported in reference 1, also a finite element model, which is numerical model reported in reference 2, and also another deep learning algorithm, which is convolutional neural network, CNN, reported in reference number 3. So if you compare their prediction accuracy in terms of RMSE and MAPE, actually our results actually are better. Based on our machine learning models outperform this analytical model, this numerical model, FEA, and also this deep learning algorithm. If you're interested in more details, you can go to you can search for this paper and download this paper, and then take a look at more details about these two machine learning algorithms, and also more details about our experiments. So to briefly summarize the first project we completed at UCF, this is the first study we demonstrate that machine learning and deep learning models can predict multiple temperature with pretty high prediction accuracy in terms of mean absolute error and also RMSE and MAPE. And also both algorithms outperform physics-based models in terms of which is actually an analytical model and also a numerical model, which is finite element model, as well as a deep learning algorithm reported in the literature. The second project I want to talk about is two-way monitoring or prediction. And the reason why we worked on this project is because the US manufacturers itself consumed almost 2 billion worth of cutting tools almost every year. And two-way causes a lot of issues, such as almost 20% of machine downtime is due to cutting two-way. And a two-way also results in poor surface finish and also pretty high power increase. And the definition of and the types of two-way. So there are different types of two-way, and the two-way describe the change of shape of a cutting tool during cutting processes due to the gradual loss of the tool material. And in this particular study, we focus on flat two-way, as you can see from the photo on the left. And in this case, in this project, our goal was to predict cutting two-way in the milling operation using so-called cloud-based parallel random forest algorithm. And random forest algorithm is one of the most powerful machine learning algorithms. And in this case, we further improve this algorithm by parallelizing this algorithm in order to further improve training efficiency, or in other words, reducing training time. So we'll first collect real-time monitoring data with multiple sensors from a CNC machine, and then store this data in a cloud system remotely. And then we build a predictive model using cloud-based parallel random forest algorithm. Basically, it's still a tree or descent tree-based machine learning algorithm. And then we predict actually manufacturing process behavior and eventually evaluate effects of different process parameters and see how which parameter may significantly affect two-way. So here's our experimental setup. So we installed 3 types of sensors on a 3-axis CNC milling machine. And you can see from the figure on the left, this is a schematic diagram of the experimental setup. And on the right, you can see the actual experimental setup. So these 3 types of sensors include accelerometer, acoustic emission sensor, as well as dynamometer. And the workpiece material is stainless steel, and the cover is high-speed steel. So the dynamometer was used to measure cutting vibration. Dynamometer was used to measure cutting force, and accelerometer was used to measure vibration, and acoustic emission sensor was used to measure the acoustic emission formed during this milling processes. The total raw data we collected is about 9 gigabytes from over 300 cutting tests, and the total time we spent on collecting this data is a little bit about over 100 minutes, and the sampling rate is 50 kilohertz per signal channel. So in other words, so every single second, these sensors will generate 50,000 data points, which is pretty high sampling frequency. In other words, we collected pretty large data sets within relatively small time window. And then after each cutting test, we also measured cutting two-way using actually a microscope. And this is an offline two-way measurement. And this slide shows some basic parameters such as spindle speed, feed rate, depth of cut, and also some specifications about the cutting tool, such as the number of flutes, the diameter of the cutting tool, the raw material, and the geometry. And here we implemented first the original random forest algorithm and evaluate its prediction accuracy in terms of MSE, mean square error, R square, and training time. So again, this mean square error, MSE, and R square. So MSE, the smaller the better, and the R square ranges between 0 and 1. So the closer R square close to 1, the better. So you can see we plotted the predicted cutting two-way versus observed two-way. Again, if all the black dots fall onto this 1-to-1 straight line, then it's a perfect prediction, 100% actually prediction accuracy. And in this case, we observed some prediction error, but which is very small. And if you look at this R square, which is very close to 1, so meaning actually the performance of random forest algorithm is pretty good. And also training time is also acceptable. So training time ranges between 1 to 2 seconds. And then we want to further quantify prediction error or prediction uncertainty. So as you can see, so there's always error associated with your predicted two-error, but how large or how uncertain these predictions might be. So we further quantified or created so-called 95% prediction interval. So for each particular predicted data. So you can see here, we plotted the predicted two-error along with the prediction interval so that we have a better idea of the uncertainty associated with each prediction. And we also observed some interesting phenomenon, which is the entire cutting to life, ranging from actually the initial two-error region right here, the first region, and then the second region is steady state two-error region, and then the third state is failure region. So you can see for this first and the third, which is last region, so we observed pretty high two-error rate. So as you can see this from this curve. And in the middle, the steady state two-error region, we observe pretty much constant two-error rate, which is very consistent with what we observe in the real-world factory floors. And then we further quantified the effect of different manufacturing parameters on two-error, so that eventually, if you want to control your two-error, then you will be able to actually find the most important parameter to control. In this case, you can see we actually calculated so-called feature importance score or index. So this index, the larger the index is, so the more important it is. Actually, it will significantly affect cutting two-error. So in this case, actually, we ranked all the features we extracted from the raw signal, and then actually in this case, actually the most important parameter or feature is the vibration of the x direction. And then we want to compare the performance of random forest with another two machine learning algorithm. One is called artificial neural network, which is also called ANN. And you can see for this neural network, actually the performance is actually worse than random forest in terms of MSE and R square. And the training time is pretty much comparable to random forest, ranging from 1 to 2 seconds. But you can see this actually the spread of the black dots actually is wider. In other words, the error is larger than random forest. We also compared random forest with another machine learning algorithm called support vector regression. Acronym is SVR, support vector regression. And you can see we also quantified the performance of SVR in terms of MSE, R square, and training time. So interestingly, you can see the prediction accuracy is lower than random forest, but the training time is also significantly smaller than random forest. In other words, SVR is more efficient, and it will only took less than 0.1 second to train a model. And then let's put all the results together to compare the three algorithms I just covered: random forest, RF, artificial neural network, as well as the previous one is support vector regression. So you can see here in terms of MSE, so the most accurate algorithm would be random forest, which is labeled by this purple curve. And in terms of R square, also the most accurate algorithm is still random forest. However, random forest, actually the training time for random forest is longer than the other two algorithms, AN and the SVR. So this motivates us to see whether we can further reduce training time for random forest in order to achieve both high prediction accuracy and also high training efficiency. So that's why we parallelized original random forest algorithm and then implemented this algorithm on a cloud system with multiple CPU cores. So in other words, we run this algorithm on multiple CPU cores simultaneously using a parallel computing architecture called MapReduce. And then this is the most specifications about the cloud node or cluster we used on Amazon. So for example, in this case, we use 32 virtual CPUs rather than a single CPU, and see how fast the algorithm can run. So here you can see this is the parallel computing results. So actually you can see after, as we increase the number of CPU cores, the training time will reduce. Of course, it's not linear relationship between the number of CPU cores and also the algorithm speed up. And this is due to a so-called pretty well-known law in parallel computing called Adam's law. Very few parallel algorithms can achieve linear speed up. But here you can see the figure, the plot on the right, we achieve pretty much a very good, almost linear speed up until we use 16 CPU cores. And then even after we start using 32 CPU cores, we can still further reduce training time, but not significantly in this case. But the conclusion is we actually implemented 3 machine learning algorithms and parallelized one of the algorithms called random forest in order to build a model to predict two-way in meeting operations. And also we further identified the effects of various process parameters on two-way in order to actually identify the most important features that can affect your two-way. This is the end of my second study. So the last project I want to cover is about chemical mechanical polarization or chemical mechanical polishing. Acronym is CMP. So this is a very important, actually, semiconductor manufacturing technique. As you can see here, the global chemical mechanical polishing market or CMP market in 2014 was valued at 3 billion. And it is forecast to reach almost 8 billion by 2026. And this is due to the growing need of CMP for wafer polishing, very high demand for consumer electronics product, and also increasing use of macro electromechanical systems or MAPS. And this is one of the figure actually showing you the actual CMP machine. And the CMP process or technique is quite complex, and it smooths the surface of a wafer with a combination of both chemical and mechanical forces. That's the reason why this is pretty complex process and very difficult to control in order to achieve high polishing quality. And in this process, CMP has been applied between deposition and patterning processes in order to remove excess materials and eventually to maintain the flatness or uniformity of a surface. And oftentimes we are talking about wafers. And this figure shows the schematic diagram of a CMP machine. It consists several key components such as the polishing pad and also the slurry dispenser and also a pad conditioner, a wafer carrier, and also wafer. And basically this polishing pad polish the surface of the wafer. And also you need another pad conditioner to refresh the surface of your polishing pad in order to maintain consistent asperities. And there are several challenges associated with the CMP technique. So the quality of the CMP process depends on multiple process parameters or variables. As I mentioned before, these process variables include polishing pressure, the downward polishing pressure you apply to this pad conditioner, and also this wafer carrier. And also relative speed between the wafer and also the polishing pad, the surface morphology of your polishing pad, and also slurry flow rate, and also the type of slurry you will be using. And these are the most important process parameters, but not all of them. I only list four of them. So the objective of this research is to develop a so-called physics-informed machine learning approach that can predict material removal rate for by combining machine learning and physics-based models. So here, the reason why we want to predict material removal rate, this is actually very important variable to predict in order to achieve very high polishing efficiency. And I want to highlight the importance of physics-informed machine learning. So you might be familiar with machine learning. You might also be familiar with physics-based models. But here we try to combine them in order to achieve better a prediction. Because as a mechanical engineer, I assume most of you guys are mechanical or manufacturing engineers. So we learn a lot of domain knowledge from our textbook and research papers. So actually, it doesn't make sense for us to just throw away those domain knowledge and simply implementing machine learning algorithms or artificial intelligence. So we should, I think the ideal case should be able to leverage domain knowledge, such as some closed form governing equations that behind manufacturing processes, and then integrate this domain knowledge with machine learning techniques. So that is the motivation, and also I think the benefit of this approach. So here, very briefly, I want to talk about this idea. I won't be able to cover all the technical details because of the limited time, but the idea is here. So we first actually developed a closed form physics-based model that governs this chemical mechanical polishing process. And these physics-based models actually involves the Cmp kinematics and also involves this so-called contact mechanics, as well as a single abrasive removal model. So by combining these two or considering these three models, we developed a closed form physics-based material removal rate model. However, in this model, there's an unknown term. Physically, this term represents the polishing pad morphology, as you can see here. And this term is difficult to measure physically. And typically, actually, people use very traditional statistical methods or empirical methods to estimate the value of this pattern morphology. And this will introduce pretty large error for this physics-based closed form model. So our idea is to use machine learning techniques, in this case, random forest, to predict or estimate the value of the pad morphology term, and then substitute the value of this unknown term back to the physics-based model. So this is the way how we combine physics-based models and machine learning algorithms. So let's look at our experimental results. So we generate training and test data using almost actually 2,000 wafers. And you can see we plotted the material removal rate versus the sample index. So you can see we used actually over 350 wafers to test or validate our machine learning model. And also we further quantified the prediction accuracy in terms of mean square error, root mean square error, and relative error. So as you can see here, we achieved about 11% relative error, which is pretty good in this case. But overall, the prediction accuracy is not as good as the previous two examples because so the raw data in this particular case involve quite large noise. So that's why the prediction accuracy is relatively lower. But in general, this is still way better than conventional physics-based models, because when you estimate certain unknown parameters in the closed form equations, you will introduce pretty large error as well. So, and then we again want to compare our model with other methods. So here we compare very conventional physics-based model called Preston equation or Preston model, reported in reference 1, published in 2017. So you can see the RMSE of this Preston model is 29.5, and our physics-informed machine learning model achieved our RMSE of 15.8, which is almost half of the other models' prediction error. So if you are interested in all the technical details about how we combine physics-based model with machine learning, and also the experimental setup about this chemical mechanical polishing experiments, you can actually download this paper from the journal, the WHERE journal, and take a look at all the technical details. The briefly summarize the third, which is last project. So we developed a new physics-informed machine learning technique to build an explainable model by combining the underlying physics with machine learning. So in this case, the reason why I think it's more explainable, because in this case, we involved actually physics behind this chemical mechanical polishing process, rather than using black box type of machine learning techniques. And also you can see here, these physics-based models was built up on kinematics, contact mechanics, as well as single abrasive removal model behind the Cmp process. And also this physics-informed machine learning technique achieved pretty high prediction accuracy in terms of RMSE and mean absolute percentage error. I think that's pretty much all I prepared for today's seminar. I'm not sure whether we still have time for questions.
Yes, we actually do have some time for a couple questions. We have about 8 minutes left. I have a couple questions. I don't know if anyone else does out there. Anybody want to?
Yes, there is in the chat box, there is a question from Mike Lisaki.
Okay.
Yeah, I see a question from Michael.
Mike?
Can the CMP model also predict across wafer planarity? I think that's important. Okay, I think the question, my understanding is if this model is generalizable. Michael, am I right? I think, Michael, you can unmute yourself.
Yeah, right. You can, Mike.
Yeah, thank you for taking my question. The model focuses on rate of removal. I was wondering if the model can be extended to think about, as you go across a big wafer. I think it's hard, isn't it hard to maintain planarity across that surface within a certain spec?
Yeah, you are right. I think it definitely can easily be implemented, and for that purpose, the only difference would be we will have to collect so-called label data or the ground truth data for the uniformity. So we have to have that data. Now we have we don't have that data. We only have a material removal rate. But if we do have that data, I think we can use some sort of 3D scanner or any a measurement device to measure uniformity. Then we should be able to predict uniformity as well, which is also very important parameter for chemical mechanical polishing.
Well, thank you for reminding me. I forgot the name of it. I think it's called within wafer uniformity. I forgot that term, so thank you.
Yeah, I think it's called uniformity.
Yeah, good, thanks.
I think because of the current how to say the customer needs on chips, the CMP process probably is even more important.
Yes.
The next question is, where do you see this research applied in industry? I covered 3 projects today. I'm not sure which one you are talking about, but overall, the methodology we used implemented for these 3 projects are pretty much the same. They are all along the lines of machine learning or AI. I do see a lot of applications. For example, some of this research were funded or sponsored by industry or by companies, and also by federal funding agencies, such as the National Science Foundation. And one of the projects, the two-wire prediction or monitoring project, was funded by General Electric. So we work with General Electric Global Research Center, developed a two-wire monitoring system. I think it looks like it's pretty useful for their factories. Any other questions?
I have a couple if we're done with those in the chat. I was going to ask about what industries, so thanks, Ernie, for doing that. that you were working with for this. So I want to try to summarize in a kind of very layman's term. What you were looking at is, let's just go to the first one. I'll just do one. Trying to simplify the overall idea is definitely to improve, is to do some predictive maintenance, to use these strategies for predictive maintenance. And the experiments that you did, I think actually were comparing AI, using AI algorithms. Some of them, I think, are available, like, quote, off the shelf, just need to be modified a little bit with your own data and situation, against some other previous modeling that people might have done. So we would predict something based on a bunch of data that had already occurred and trends that were happening just with an equation. Even a y equals mx plus b kind of equation, we could predict out farther on our axis. So you're kind of comparing traditional modeling, let's take that first case, with the use of AI in order to get a better, look like better predictions for the wearing of these tools. Is that?
Yes. Yes. So yeah, because most people might be familiar with statistics. So actually, so these studies, of course, you can use different methods, different algorithms, different tools, such as even conventional, let's say, very conventional linear regression. You can also achieve predict something, but here, as the advancement of AI techniques, so basically the prediction accuracy has been significantly increased over the past few years. I'm not saying conventional statistical tools are not useful anymore, but AI relatively, I think, more accurate. Also, it depends on the quality of data. But here we are trying to, so some of the methods, so you can implement and find those existing open source library, off the shelf library. So you don't have to really reinvent the wheel by developing new algorithms. But in our research, oftentimes actually, we try to improve existing methods and implementing those methods in a more efficient way. That's why we developed so-called parallel random forest by improving training efficiency and also improving integrating physics with machine learning algorithm, try to improve prediction accuracy. So in other words, our goal is to both improve prediction accuracy and also improve prediction training efficiency by utilizing existing machine learning techniques.
Okay, awesome. Thank you. So,
and by the way, actually, I forgot to mention, one of my graduate students actually is working as full-time intern in a pretty large semiconductor manufacturing company, just actually very close to Orlando, I think in the suburb of Orlando. And that company actually is trying to hire more data scientists with mechanical or manufacturing domain knowledge or background. And I think they prefer to have such type of skills, which might be useful information for educators who are in this Zoom meeting, maybe to help their students to learn more, which can help them maybe get a job in the future.
There you go. It's always good to get a job. All right. Thank you so much, Dr. Wu. We have just like 1 minute or two left. I want to tell everyone, thank everyone for attending today. If you have any additional questions, you can email to me at flate.org, and we will be posting the recording of this and hopefully the slides, if you'll send those to me as a PDF, and get that out to everyone. Again, there was a lot of information about using AI, but it's kind of important to see that it goes way deep into the process. In order for anything to get implemented in manufacturing, we do need to make sure that it's a better process than the old processes that we have been using, and that we can improve our OEE, our overall equipment efficiency, and reduce our our costs. and wear on our materials and our tools as well. So thank you again. We do have one more session, one more Tech Talk this spring. We'll just have a kind of summary wrap up of our 3 speakers this fall and spring to talk about their work in the bigger picture of smart manufacturing going forward and some of the issues engaged from their different points of view. So you can join us on April 15th, and I look forward to seeing all of you then. Have a great Friday afternoon.
Thank you so much.
Thank you, everyone.
Yeah.
Bye-bye.